Welcome to the Qiskit Quantum Seminar, where we bring you the latest and up-to-date research in the quantum world, here on YouTube, live at noon on Fridays, Eastern Standard Time. I'm your host, Nick Braun, coming at you from the IBM Quantum Studio in Grand Central Terminal, New York City. While we're on that, before our speaker starts, maybe you can drop a line in the chat and tell us where you're calling in from. It's always nice to see what a diverse geographic audience we have at us today. And we've got San Diego, sunny San Diego. How's the rain out there? I know you've got a little bit of a what do they call that? Tropic thunder. I don't know. It is not as nice here in New York today. It's a little gray. Okay, we've got sun, Portland, Oregon. We have Massachusetts, Ecuador. That's great. So we've got is Ecuador? Are you south or north of the equator? Frederick, Maryland. All right, so we got some East Coast people. Taiwan, wow, it must be really late. I admire your ability to watch this late at night. We've got Toronto here, Chile, some more South America, India. We always have a lot of people from India. That's great to hear. Poland, wonderful. That's really great. We have Montreal. We have a lot of people coming in today. And so maybe now's a good time to note is that while this seminar is going to be recorded, you can only ask questions in the live chat, which I will be moderating here. So please, after I introduce the host and we get into it, feel free to drop your questions, and I will let Amira know about it. We've got a few more: Israel, Sri Lanka, Germany, another India, the UK, Turkey, a Bosnian from Turkey, Belgium. Okay, Hong Kong. This is a great audience. So I'm very, very happy to know that we have so many people coming in from the world, and especially those of you spending your Friday night with us today. The ATL, good job on the Super Bowl. Okay, so I guess I'll get started with that. So today we have a delightful guest, someone I haven't seen for a while, since before the pandemic, Amira Abbas, and she's going to be telling us about on quantum backpropagation and information reuse. So Amira is a postdoctoral researcher at the University of Amsterdam, as well as QSoft, a quantum computing research institution in the Netherlands. She was previously an intern at Google Quantum AI and a pre-doc researcher at IBM. She holds a PhD in quantum computing from the University of KwaZulu-Natal, during which she was a recipient of Google's PhD fellowship and the Oppenheimer Memorial Trust Award. Welcome to the Qiskit Seminar, Amira. It's great to see you again.
It's good to see you too, Nick. Thanks a lot for having me. I'm really happy to be here.
Absolutely. So go ahead and take it away. I'll let you know when we have questions.
Okay, wonderful. Thanks so much. And yeah, thanks for everyone for attending and tuning in. And yeah, that's super, it must be super late. So well done. I've attended a few of these seminars myself, and I find them always super, super interesting, but also very physics related. And today, while I will tell you a lot about physics, I'm also shifting gears a little bit into quite a bit of machine learning. And a lot of the motivation for the research that I will tell you about was really from understanding questions that we were wondering about in a machine learning setting, importing them into quantum. So if you want to follow the paper at home, here's the archive number. And this is some work that appeared in Europe's last year. And here are some of my amazing collaborators from the team at Google and Caltech. Okay, and yes, at any point, if there's something's unclear or there's some questions, please pop them in the chat, and yeah, Nick will get to it, or I will answer it at the end. Okay, good. So, the title might already give away the opening question that I kind of want to pose to you. It's like, if you look at this deep learning timeline, right? So now we're in this new age of AI and all these amazing models, these large language models like ChatGPT with billions and billions of parameters, right? These models are just super, super large. How did we get here? We started with the concept, the theoretical concept of neurons. The perceptron model came around, but really, how is it that machine learning and deep learning and this new era of deep learning, how is it so successful? And in particularly, what is the key to scaling our best machine learning models, like neural networks in practice, is the question. And of course, my answer is a little bit subjective here. It has a lot to do with the title and what I'm going to tell you about. But I really think that the key to where we are today is a combination of two things. One, the ability to have large computers, so that we actually have good hardware with good computing power. We also have this algorithm called backpropagation, which has been quite a game changer for machine learning. And backpropagation really, in my opinion, was the thing that allowed us to have models at scales we see today, these really, really large scales with billions and trillions of parameters. Okay, so what is backpropagation? In a nutshell, if you have a machine learning model and you want to be able to train it to learn from data, you need to do optimization on this model, right? You need to go and tweak those parameters in your model for your model to be better. And the leading way to do that at the moment, classically, is through gradient-based methods. So computing the gradients of functions and using the gradient information to figure out how to optimize a function. So backpropagation can just be thought of as a recipe to compute gradients of a specific function. And it does so in a beautifully computationally efficient way. And we'll talk a little bit more about this computational efficiency a little bit later. But it is, I think, the first method that was proposed to be super, super efficient in calculating gradients for a neural network. And I think a lot of classical machine learning people miss this point of, if you're familiar with neural network functions and how they look, you might naively think, oh, well, there's so much redundancy in a neural network function that if you write out the derivatives, there's so much repetition in these derivatives that it's like kind of just the chain, due to the chain rule, like writing out the derivatives, that propagation achieves this efficiency, it's just the chain rule. But it's a little bit more elegant than that, like backpropagation, yes, exploits structure in a function, but it also kind of, as it computes a function, stores information, intermediate information, such that it can be reused to compute gradients. And it's really this information reuse that allows this efficiency in the backpropagation algorithm. Okay, so let's talk about this efficiency a little bit. And I think, this is probably the main thing to take away from today's talk. At least to me, it's the most interesting. So when I talk about backpropagation being computationally efficient, I'm really talking about how resources scale. And in computer science and things like that, we care about resources like time and memory, computational time and memory to compute something. So now imagine I'm given a function that depends on some parameters. So this function, let's call it f, and theta here is like a set of parameters. Right? So you can think about it as a very long vector, for example. So if there's m parameters in your model, you can think of this as like an m-dimensional vector. And m, of course, can be super, super large, right? Billions, if not even now, like billions. Okay, so what backpropagation does and efficiency gives us is it says, if I want to calculate the derivative of this function with respect to this parameter set, so this f dash of theta is, you can think of it as a gradient vector, right? And we'll have m entries in it, so it's a very large vector as well. If I want to estimate this gradient with some precision, then I can do so with time, computational time to compute the gradient that is less than or equal to some small constant times the time to just run the function, right? So let's digest that a little bit because I think this is important. So what is that saying? That's saying that the time it takes me to compute the derivative of a function with respect to every single parameter, with respect to every single component, right? And there's like trillions of these parameters. This scales roughly proportionally to the time it takes me to just run the function once, right? And 1 and 2 are just like small constants, small numbers. So that's quite amazing, right? Because you would think naively to compute each gradient, it would take you you'd have to kind of estimate the function for each of those gradient components. So the fact that you can achieve roughly the same time for both, just running the function once and computing all its gradients, is really amazing and really owed to backpropagation. And the same is actually true for memory as well. The memory it takes me to compute the gradient roughly is proportional to the memory it takes me to just run the function. And this is really because this is this efficiency that I spoke about earlier about being able to store and reuse intermediate information. And this is for networks. What's even more remarkable is these constants are actually really small, right? They're a factor of 2 or 3. And this is proven already. This is the overhead that we're dealing with. Okay, so that's really cool and that's really nice. But of course, for us in the quantum realm and in quantum computing, the most natural question is, well, can we achieve this kind of backpropagation scaling in models that we want to use for things like quantum machine learning with quantum computing. So for quantum models, can we attain this efficiency? And even if we relax this assumption, this strict assumption that C1 and C2 have to be really small numbers, maybe we can allow them to have some sort of logarithmic dependence on the number of parameters, right? So M is the number of parameters. Maybe they can, depend vaguely on this. Can we get close to like some sort of relative overhead of resources like this? And I also want to just point out, like, before we went into investigating this question, all of the methods to compute gradients of quantum models for machine learning in literature do not achieve this beautiful scaling that we see with neural networks and backpropagation. So this is actually like a fundamental problem that we need to address. Okay, so that's the research question. Can quantum models achieve this kind of scaling? Now let's talk about the types of models that we considered. And I think, for those of you who are in quantum computing, in quantum machine learning, you will be very familiar with these parameterized quantum models. They go by very, very different names, variational circuits, quantum neural network time. Really, they're just parameterized circuits, right? And they take on a specific form. So now let's say we're dealing with this set of quantum models, and I'll describe exactly this function. Theta, again, you can think of as a set of parameters. And in the quantum setting, the function usually takes on this form where, if you're familiar with quantum mechanics, that's great, like, you know this equation. But if not, like, how I like to think about it is like, this is just a vector that depends on parameters. And we're usually interested in measuring some observable, right, which is just a matrix. And then this is the vector transpose, complex conjugate transpose. So it's kind of just vector matrix multiplication that we're dealing with here. And in that, there's like parameters that we can optimize for. And these models come up in areas outside of quantum machine learning, right? I just want to briefly say that they're not just things that people try to do for machine learning. They're also quite natural in other settings. Like, for example, quantum simulation. Let's say you want to like learn some ground state of some Hamiltonian or something like this, and you prepare a state and you try to like get to a target state by tweaking and optimizing parameters to move your state iteratively to some target state. There's also, motivation for these types of variational sets, parameterized models in fields like optimization, where people try to encode very difficult, usually combinatorial optimization problems into these variational circuits. And the hope there, I think, is you can maybe make an impact in fields like logistics and finance and so on, where optimization problems come up quite a lot. And then, of course, machine learning, quantum machine learning. Where the idea is that, maybe the output of this function is interpreted as a label or, something for a machine learning task that's useful. And I think the hope is that perhaps this model is more interesting or expressive in some way or form, right? So I'm in no way like advocating that this is the way to do quantum machine learning, but this is a very popular approach. And so, in short, people, what I want to say is that people care a lot about these models. They're very popular. And so if people care about these models and they are parameterized and rely on optimization, we need to be able to optimize them well, right? We need to be able to optimize them as well as state-of-the-art optimization and our leading models there. And so, I alluded to this earlier, the way people do this classically is through gradient-based methods, okay? So again, let's talk about the nuance of quantum gradients, right? Or can we even calculate gradients with respect to these models? Let's, to answer this question, let's go through a very basic baby example, like a kindergarten example. And then we can like start to build an intuition for why this is a little bit more nuanced in the quantum thing. So let's imagine our initial parameterized state is quite easy to construct. So let's say we've just got one qubit in our system and we know that that qubit is in state 0. And then we apply a parameterized rotation to this qubit. We're rotating it about a certain axis. And so our parameter theta controls the angle of the rotation. So it's just a scalar value in this little toy model. We just have one parameter. And, we can even draw the circuit for this, right? It's pretty easy. We have like one qubit and then we do some rotation about some angle. And then if we wanted to, this is a very clear description, right? We could even write our derivative of this thing. it takes a very nice, easy form. We just drop down the minus I x if we're taking the derivative with respect to theta. But if we write out our full model, let's say that we want to measure like in the Z basis, okay? So our observable of interest is just like the Z matrix or the Z operator. And so we can write like the full model out, like our full function f of theta that we want to estimate, for whatever purpose. And it looks like this, right? And then we can write out the derivative of this thing, right? It's very clear, it's very easy. We can use the product rule to write out and expand, the full derivative. Okay, good. So that's the derivative with respect to the parameter. And let's say to simplify this calculation, we just set the parameter value to 0. We set theta to 0. And what do we get? You can just take my word for it that it reduces to this quantity here, which all I want to show to you or illustrate to you is that it's an expectation value with respect to operators that don't necessarily commute. Okay, so we're going to need to estimate like expectation values of non-commuting operators. And that's just for one parameter, right? So if we now had a model, let's say with 2 parameters, so let's say we do a rotation first about the y-axis, and then we do a second rotation about another axis, the x-axis, and we have 2 parameters in there, theta 1 and theta 2. We can go ahead and measure again in the same basis, and we can write out the derivatives with respect to each parameter. You can just kind of take away that this is how it looks and simplify trying to estimate these derivatives by setting the parameters to 0. And what that reduces to is, again, estimating expectation values, but not necessarily the same expectation values. And importantly, not necessarily with respect to operators that commute. Okay, so you can kind of get a sense for why things are a little bit hard, right? We need to estimate expectation values. And how do we do that? We typically run a circuit and we measure, and then we sample, like we do the sampling, this repeated measurement, and running the circuit process over and over. And so like, if we had to do that several times for every single parameter, start to build up. And so, estimating, if there are m parameters in our model, estimating m gradient components roughly corresponds to the task of estimating m expectation values with respect to operators that aren't easy to group together and measure in the same basis. Okay, so more formally, let's talk a little bit about how we think of time in our quantum setup. And to do that, we need to talk about like a cost model. So how do we account for like computational cost in terms of time? So for I think for just ease of study, kind of assumes that every parameterized operation that I want to perform in my circuit, my model, and its inverse just costs me 1 unit of time, right? So one unit cost to apply every parameterized operation and its inverse. So for example, if I just use some shorthand notation here, theta again, is a n-dimensional vector. If I have a model that applies, this u of theta, it consists of basically m parameterized operations. So these uj's are each a different parameterized operation, and it depends on a parameter theta j. Okay, so there are a product of m of these parameterized operations with different parameters. And so if I wanted to create a parameterized state by applying such a series of parameterized operations, how much would this cost me in the cost model? Because like if each parameterized operation costs me 1, and I'm applying m of them, then it should cost me m, right? And it does. Like this is how we think and account for cost. So it costs me like m computational units. And if we had to imagine how much it would cost us to estimate our function in this regard, where our function does a similar thing, it like applies all these m operations to some initial state, does a measurement, and the adjoint, the inverse also costs us unit costs, like applying those inverse operations. So to estimate this function would also cost us roughly m units of computational time according to our cost model. But as I mentioned earlier, like, to estimate this true expectation value, we kind of have to run the circuit multiple times to get a sense of this average. And so usually there's like sampling error that comes into it, right? We have to sample multiple times from our quantum circuit, our quantum model. And so like there's usually some notion of like an error, which we can kind of ignore for our purposes, because what we're really interested in is like the scaling in the number of parameters, because this is the thing that blows up as we scale our models up. Okay, so this is to estimate our function. And if you remember from the backpropagation scaling, the whole goal is to try and get the time it would take you to estimate your function to equal the same as the time it would take you to compute gradients. So how much time does it take us to compute gradients? Well, naively, if we had to write out the derivative with respect to one parameter, let's say theta k, so the derivative of this function with respect to one parameter, it kind of, if you stare at it for long enough, it kind of almost looks very similar to the function itself. Like, there's like almost an identical form here with the subtle difference of like this partial derivative with respect to the kth parameter coming in. And so if you had to like count the operations that are being applied here to estimate gradient equation, it also is roughly like n units of time. But the problem, or the catch, is that this is just for a single gradient component, right? And we have m of them, so this is just for one. So if we wanted to estimate full gradient component, we would have to do this m times, and so now we get a cost that is like m squared, okay? And that's to compute our full gradient. And if you remember, like, the time that it takes to compute the gradients, we want it to be roughly the same as the time to compute the function. So there's like an additional factor of m here that we need to get rid of, because classically this is not there, right? So classically for neural networks, these things are roughly proportional, roughly equal. And you might think, well, this is just like a linear scaling in m, like how big can it be? Like it's not such a big deal, right? But in practice, it is kill quantum machine learning models of this form, because we will never be able to scale and compete with neural networks, state-of-the-art neural networks. And here's a little picture to kind of motivate why. So these red crosses are if you had what is called the parameter shift rule available to you to compute gradients. So this is how people actually compute gradients at the moment. It has this this bad scaling that I showed you here with the m squared. Okay, so parameter shift rule scales quadratically in the number of parameters. And if we had a notion of backpropagation, quantum backpropagation, that didn't have this bad scaling, then we're in the green crosses. And this picture here basically says on the x-axis is how much time you would have available to you to train a model. And then on the y-axis is how many parameters you can achieve with so much training time. So for example, just like, on your computer, if you had 1 day to train a model, if you had this bad scaling, right, if you do it the way people do it right now, you could only train a model with 9,000 parameters. Whereas if you had backpropagation scaling, you could already go up into the millions. So 9,000 parameters is like a joke these days, right? There's nothing really that we can do interesting in this regime. So we really have to get better scaling in the way we do gradients. Okay. All right, so now I can tell you a little bit about some of the results that we found and deliver the intuition as to why these results are the case. And then, we can also talk about some open questions, and I would also love to hear some opinions from the audience around this. So in order to prove and say things about whether backpropagation scaling is achievable, we needed to kind of divide into different settings, and the settings that we consider, so always the same types of models that I presented to you, these variational circuits, these parameterized quantum circuits. But there's a couple of things that you can assume about the model, right? So like the first assumption you can make, for example, is that your input state that you're given is entirely known to you, right? So like in the baby example that we went through, we kind of knew our starting point was the 0 state. So you can make the assumption your input state is known, maybe it's the all 0 state, and then you apply parameterized operations to it. But you can also assume something more general, right? You can assume that an input state is entirely unknown. Maybe it just comes from some experiment in a lab, and you're just given some input state, and then you apply some parameterized operations to it. So you don't know anything about an initial psi, you apply some parameterized operations, and then you get a parameterized quantum state. And then on top of those different types of assumptions that you can make, you can also assume that you only have the ability to measure single copies at a time. So So you can only like, run your circuit, measure it, repeat the process. You can only measure a single copy of your quantum state or your quantum model, however you want to think about it at a time. But of course, like a more general ability is if you make the assumption that you have access to multiple copies of your state at a time. So imagine then making like a big measurement over a tensor product of copies of your state. So this is something we talk about and refer to as the quantum data setting, because you can imagine that you're given like lots of copies of your quantum state as quantum data. Okay, so there's a couple of things that we can immediately say about certain settings. And so, for example, if we assume the input state that's just given to us, we apply some parameterized operations, and then we can only measure single copies at a time, then there is a result that shows that unfortunately backpropagation scaling in general is not possible. So we can't achieve this very nice scaling that we see with neural networks and backpropagation. And this is a little bit sad, right? Because if you think about this setting, it is ultimately like the most realistic one, and the one that we would want in nature, right? Because we don't necessarily want to make any assumptions on our input state that we start with. And usually, I think in the lab, when people actually like run experiments and stuff, the most reasonable thing to assume or do is single copy measurement, right? So in some sense, it's a bit sad because this rules out something rather practical. And a way to see this for those who are interested, like, comes from this very nice paper that is linked below. And you can kind of take a very simplified case to show that in general, this task of achieving propagation scaling is not possible by taking your parameterized operations to just be Pauli operations, right? So you perform parameterized Paulis in your circuit, and you do that simplified trick of setting the parameters to 0, and then it reduces to a task for which we have a sample complexity lower bound. And we can use this sample complexity lower bound to kind of infer the cost. We can see this is how many times we have to sample to solve this task, which corresponds to like estimating gradients in this simplified setting. And unfortunately, it gives us this bad scaling again. It gives us this quadratic scaling in the number of parameters that we don't want to see. Okay. All right, so we know that this is kind of a no-go. But what about in a little bit more restricted setting where I know my input state, right? So I actually know what it is. Does this help me in any way? And unfortunately, one can also go through like some computational arguments to show that even here, it's not likely that one will achieve backpropagation scaling. And how to think about this is like, imagine that you have a quantum state that, let's say, realistically comes from a circuit of polynomial complexity. So what does that mean? Basically means like if you have some state, then it's generated in the circuit. Let's say we fix the gate size of the circuit and the gate set. And let's say we like to create this state of polynomial complexity, we basically just apply gates from this gate set that scale polynomially in the number of qubits. Okay, so this is what we mean by a polycomplexity circuit or polycomplexity state. And you might think, well, maybe I can explicitly learn this state or reconstruct the state so that I can do backpropagation more efficiently. And indeed, like some recent results, like classical shadows and stuff like that, kind of tell us that we can information theoretically efficiently learn this state, right? If it comes from a circuit of polynomial complexity, we should information theoretically like be able to efficiently measure it a number of times such that we can learn it. But unfortunately, in general, the task of like identifying the state is still computationally hard. So even though like number of measurements is not too wild or too like ridiculous that we have to make to the system, there's still some computational barriers there. And how to see this for those who are interested, like this part I think is not pivotal to the rest of the talk, but just for completeness, I think it's a nice statement. Is if you had a state that came from polycomplexity circuit, so a circuit consisting of polynomially many operations that scale the system size, then you can actually write down how many possible circuits there could be, right? So let's say there's k of them. K and n is the number of qubits, and p of n is just like some polynomial in the number of qubits. Okay, so this is like n to a polynomial in n, so it's still exponential in the number of qubits, right? So there's exponentially many possible circuits that our state psi could be generated from. There's lots of them. And so we could actually like write down the states, not write down, sorry, because let's just label the states by 1 all the way to 5K, right? So let's say every possible state that can come out of every possible circuit of polynomial complexity ranges from phi1 to 5K, okay? So what we can do is we can use this really nice classical shadows method, basically estimate the fidelity, right? So we want to overlap with our with each of these possible states that our state could be, right, with our target state psi. So we want to estimate the fidelity with respect to our target states, and each of these possible circuits can be generated from circuits of polynomial complexity. So this classical shadows method allows us to do that. And remember, like, we're estimating now the fidelity with respect to like a super, super large number of states, right, exponentially many. But the beauty of classical shadows is that we can actually do that with only a few measurements. Like, we only need a logarithmic number of measurements, log k. And k is exponentially in n, but if we're taking the logarithm, then we're still at k, right? This is still reasonable. So the classical shadows method is amazing for that reason, is that like information theoretically we can measure efficiently, and we should be able to like find a match for our state psi, because our state is one of these phis. So there should be, a fidelity 1 match with high probability. Okay, but the catch, of course, is like, in the worst case, searching over all these fidelities to find out which of these phis our psi, our target state is generated from, or is a match with. In the worst case could require exponential time. So there's still like a problem there computationally. Okay, so long story short, that whole segue was basically trying to motivate and show you that even in case that when your input state is known, things are still kind of hard in general. And also kind of iterate through other known gradient methods to show that like these also do not achieve backpropagation scaling. Okay, so that seems a little bit negative, right? So it's like, in this realm of single copy access, it seems unlikely that we're going to see backpropagation scaling. So of course, like the natural extension. But before we go to the natural extension, pause and think to yourself, like, why is it not so straightforward? Especially since there's so overlap in the actual math, right? Like if you write out this function that we want to estimate, and also its gradient components, there's so much overlap in here, right? There's so much information that's being, like, computation that's being repeated. And in the spirit of backpropagation, it should be, there should be a way to try and use this repetition of computation such that we can do better with gradients, right? And so why is it not so straightforward? And the reason is largely due to quantum phenomena. It's like the fact that when we measure our system, we destroy quantum information, right? We destroy all our information, so we can't reuse things very easily. So the idea of allowing access to multiple copies of your state, the intuition for why this is interesting or why this should maybe work and help us a little bit, is that you can design measurements that are a bit more clever. When you have multiple copies, you can design measurements such that you can get information out about to compute gradients, and you don't necessarily destroy all the quantumness of your states. So you can kind of reuse them again. So by allowing access to multiple copies, you can kind of reuse information if you design measurements in a clever way. So this is the intuition about why having access to multiple copies is more powerful and perhaps more helpful in our situation of where we need to reuse information. And drawing on some of the success of multi-copy measurements and having access to this model, there are also other papers that kind of prove separations of learning tasks. Like there are things that you cannot learn or not efficiently learn if you do not have this ability to measure on multiple copies. So if you can only measure on single copies, there are like clear learning separations for these two models. And something that's immediately quite cool is that if we go to the simplified setting of computing gradients, where we have parameters in our model that are parameterized Pauli operations, and we do this thing where we set the parameters to 0, we can actually then show that we can estimate all the gradient components and get a scaling that is in line with our definition of backpropagation scaling. So this is already quite promising. Like just by allowing access to multiple copies, and we're doing parameterized Pauli's, and we're setting them, setting the gradients to zero, the parameter value to zero, then we can already we can already achieve backpropagation scaling, which is pretty cool. But when we try to generalize the model a little bit again, so we move away from Pauli's, maybe estimate the gradients at parameters that are not zero, then things break down again. And
sorry to interrupt, but I think it's on a lot of people's minds is how do you do this? How do you create multiple copies without violating the no cloning theorem?
Yes, excellent question. And I think in my head, how I imagine it is like, and Nick, you could probably also answer this question, is like, imagine instead of, typically when we think about things, we always think, okay, we start with like some basis state that we know, we apply some operations, and then we get like, some other quantum state, and then we do measurements, we have something classical in another basis state. But imagine you have something more general at your disposal, like something that just is some natural process that spits out quantum states and gives you states, right? So it gives you copies. And what this could be is like, some experiment that you set up in the lab that produces a quantum state and can be run multiple times using the same dynamics. So indeed, the no cloning theorem, is a real thing. We can't like, given a copy of a state, copy it multiple times and store it. But we can make assumption we have some natural process that like gives us the same state, and this is the kind of thing, this is the setting I mean, that like we have access to multiple copies of a state. So you can imagine some natural process that spits out a quantum state and can spit out, the state multiple times by running this process over and over. Right. So in that way, yeah. Yes.
So if I can paraphrase that, would that be like you can do identical preparations to generate these states?
Exactly. Like that's how I think about it. Yeah.
Okay, great. Thank you very much.
Okay, cool. But yeah, maybe that's a good point to also highlight that, things like how to store these copies in memory and keep them coherent and call on them, and this idea of quantum memory and all this kind of stuff, I think from a hardware point of view is still like very tricky to do, right? Even making a big measurement over multiple copies, I think is very, very hard to implement. So this idea of having access to multiple copies and design measurements in a more clever way, I'm really speaking from a fundamental theoretical perspective. So like implementing it could be a totally different disaster on its own. Okay. All right. So when we move away from this restricted setting and we still have access to multiple copies though, things still break down. Like the scheme that worked here to give us backpropagation scaling in this special case does not work anymore. And so we kind of have to ask ourselves a question about just how hard this idea of computing gradients is in this framework, right? Like well, not computing gradients, but achieving the backpropagation efficiency that we want to achieve. How hard is it to get there? And what we noticed, I think is quite cool, is that there's actually a very deep connection with this task of computing and estimating gradients of these parameterized models, and another problem that comes up in quantum information theory quite a lot called shadow tomography. So shadow tomography was proposed by Scott Aronson, and if you're not familiar with it, I think I'll just recap it very quickly. How it goes is, imagine you have a class of 2 outcome measurements, okay? So, think of it as a set of measurements. And now you're given a certain number of copies of an unknown state, okay? So you're given copies like exactly how you just described it, like you have some sort of process that spits out m copies for you. And you have knowledge of measurements that you want to make on your state. Okay, so you know that there are these E's, E1 to EM, which come from your set of measurements. You know these measurements that you want to perform with respect to your quantum state. The task of shadow tomography is to output estimates that closely, that are close to these expectation values that you perform. So the measurements with respect to your unknown state. For every E, okay, so there's M of them, and you want to output kind of estimates for these true expectation values such that you don't use a large number of copies, okay? So you want to minimize the number of copies of your state, okay? So this little m here is the number of copies. You want to make this as small as possible while still being able to estimate expectation values you're interested in. And if you think about computing gradients, that's what we're doing, right? We're estimating expectation values. And so if you imagine like these E's to, naively kind of be ways to extract gradient components, then these problems have a correspondence. The shadow tomography problem and computing gradients have a very nice correspondence. So we actually formally show this reduction, that basically if you can solve the shadow tomography problem, if you could, let's go like this. If you could estimate all gradient components using m copies in a certain runtime, then you could essentially solve the shadow tomography problem as well with respect to a certain class of observables. And yeah, and I think to show this quite nice, you can define a more general model, which we don't have to spend too much time on now, but call it a quantum neural network, can put a bunch of parameterized operations in there, measure some observable, and show this correspondence. But the nice thing, and the last thing that I'm more or less going to say, is that since this shadow tomography problem has been around for a long time, one can port ideas and results from there to do more efficient backpropagation, right? Of course, is there anything we can leverage from there? And so indeed, one can actually come up with a very nice explicit algorithm that estimates, these are just derivative components, gradient components of our function, just I've written it a little bit differently, but ultimately the same thing we're interested in. We can come up with estimates for our gradient components using a number of copies of our state, such that if we plug it back into our cost model, we get something in line with backpropagation scaling. So long story short, we can use shadow tomography, results from their explicit algorithms to do better in our time complexity for quantum backpropagation, or this backpropagation scaling of variational circuits, which is awesome. But there is a huge catch to the algorithms that work for shadow tomography, and that is that they require exponential memory. So they still fail on the memory requirements. Remember from before, like this beautiful backpropagation scaling holds for both time and memory. And unfortunately, for this algorithm to compute the gradients to succeed, it requires storage of a classical density matrix that just scales exponentially in the system size and the number of qubits. And so this is just not going to work from an implementation point of view. And the reason why, I just put a snapshot of the algorithm. If you're interested, I can point you very much to the paper. But the reason why is really because we have to store a sort of hypothesis, like a guess for our true state in classical memory. And this hypothesis state is super expensive, right? It's going to scale obviously exponentially in the number of qubits. Okay, so to sum up, I know I've said a lot of things here, but basically the takeaways are quite simple, right? So if we're in the state where we have single copies, like this, we have single copy access, we know the input state, there are computational arguments that kind of, point to the idea that backpropagation scaling is not feasible or achievable. If we are in a more general setting where we, have no idea about what our initial state is, there is like a hard limit or information theoretic lower bounds that tell us backpropagation scaling is not possible in general. If we move to the multi-copy setting, whether we know our state or not, we propose a time efficient in line with backpropagation algorithm that calculates gradients, but unfortunately the memory fails. And in general, one cannot remove this. This is going to be like a hard barrier. So there are a ton of open questions, right? So even though this is a barrier for these variational models, as a researcher, this is also an opportunity, right? How do we overcome this barrier? How do we find an efficient scheme to compute gradients of this form? Is that even possible still? Maybe everything I've spoken about has been with respect to worst case scenarios. Maybe there are special cases or classes of parameterized models that still scale well, train well, and are expressive or interesting for machine learning. Or maybe it's time to think about other model types, and I would really love to hear from people about what ideas they have for quantum machine learning models outside of variational circuits. Perhaps different methods for optimization are just what's needed for these quantum models, because so far everything I've discussed has to do with computing gradients, and maybe there are more sophisticated ways to do optimization other than gradients that work for quantum models as well. Okay, good. And with that, I would like to thank you all for tuning in, and yes, I'm happy to take any questions if there are any.
All right, thanks so much for the great talk, Amira. That was super interesting, very forward-looking and exciting applications of quantum computing. I'm going to go ahead and encourage you to, if you have any additional questions, to drop them in the chat. But we did receive a number of open-ended questions during your talk that I wanted to save to the end, so I didn't railroad you too much. So maybe the first one is, we were talking about scaling, and there a question came up with, as regards to classical backpropagation, is there an intuitive heuristic explanation for the scaling classically? And then maybe I could add, how would you relate that to the quantum one?
Yeah, so I think the beauty of why the scaling works classically with neural networks is a combination of the fact that there's a lot of structure in a neural network function, right? So if you actually write down the function, you'll see there's a lot of, when you write down the derivatives of this function, you'll see there's a lot of repetition in the computation with respect to each derivative. And through this repetition is really how backpropagation exploits being able to save intermediate information as you compute the function to achieve efficiency when you compute the gradients. So it's like through this this idea of having white box access to your function with a lot of structure, and then being able to store into information. This is absolutely crucial for a neural network to achieve this efficiency, because being able to store this intermediate information really allows it to be reused to compute gradient components. And through the repetition in all these derivatives of the computations, you can estimate little pieces of your function, use them for gradients, and get really nice scaling out. So this, I hope, delivers the intuition for why it works classically so well.
All right. That's very, very interesting. Okay. So here's one that I'm not really familiar with, but I noticed, because I was looking around the internet, that some of your collaborators have worked on this. And it was that the question was, could you dequantize the circuit into an approximation to perform backpropagation? So I guess the thing is, like, dequantization, are there shortcuts to realize this classically?
Okay, so maybe I should clarify something here. So one can always implement the actual backpropagation algorithm that you have classically. So this might sound a bit confusing at first. So backpropagation is an algorithm that computes gradients and then kind of propagates back, in the network, and optimization happens magically. And one could, create a quantum circuit that, with some extra space, allows to do a similar thing. You could implement, technically, you can implement any computation you can implement classically on a quantum computer with enough space and time. So you can run a neural network in principle and do backpropagation as well. But what I'm talking about today is achieving the same scaling of gradients with respect to a very specific class of models that are these variational circuits, right? And so if your models look like these variational circuits, computing gradients for them naively just corresponds to sampling. And this idea of an actual backpropagation algorithm is not really applicable here in this variational circuit kind of thing. It's talking about a very specific form of function and computing gradients with respect to them. So indeed, you could implement neural networks, implement backpropagation on a quantum computer, but it requires resources that don't match the resources that you see on a classical computer when you do backpropagation with neural networks. And again, the reason is because we can't store quantum information and reuse it nicely. Yeah.
Right. Okay. Great. There was a follow-up on the backpropagation scaling, and that was, does the scaling depend on the depth and the width of the network, or how does the scaling depend on the width of the network?
Yeah, good question. So the scaling depends on the number of qubits. I think if we go back, here we go. So the number of copies we need kind of scales linearly in the number of qubits. A little n is the number of qubits, and then polylogarithmically in the number of parameters, and then times an additional factor of m here, right? So overall, it's kind of quasi-linear in capital M, the number of parameters. So in terms of depth of the network, I mean, it depends how you put your parameters out, right? Like, so how you spread your parameters around. And so like in our cost model, we kind of just imagine just counting every time we apply a parameterized unitary, and we don't really think about this concept of depth. But naturally, as you have more and more parameters, you know, you're probably going to go to higher depth. So this is how I guess you can think about depth. And width, yeah, I mean, it scales kind of linearly in the system size. So that's good, I guess.
Great. Thank you very much for that answer. Here's a very open-ended one, and that is, are there ways to manage the space complexity in large QML systems? I guess that's the
good question. Yes, yeah, that's a really good question, and something that, you know, I should have maybe put as an open question, because, you know, the algorithm that we describe is something that requires storage of a classical density matrix, but maybe there is a cool way to kind of store a description of your unknown state in a more efficient way. Like, for example, there are quantum states that we know of that can be described classically. We can write them down in a number of that don't blow up. You know, there exist states for which there are efficient classic description. So maybe one way around this like memory issue that we see with our approach is to just think about nice ways to approximate general quantum states on a classical computer. And this is I think where this field of like tensor networks and all these kind of come into play, like trying to develop approximations for quantum states and quantum systems that are efficient classically, and so we can do better simulations.
Yeah, okay, that makes a lot of sense. There's a number of things about, could you do things about like model compression, or you could look at sparse models. I think you're kind of alluding to this in a way to make it approximate. So I think you kind of answered that already.
Another, I think maybe also another, I think maybe also another point about model compression, because, you know, a lot of people also acknowledge that training quantum neural networks or quantum circuits, however you want to call them, training these models at scale is maybe not necessary, because maybe these models can be pruned or, you know, compressed into fewer parameters and do the same thing as these large neural networks. And I mean, I guess the answer in principle is it could be, right? It could be. But the point that we're trying to make here is that this backpropagation scaling of resources, you know, getting this like proportional cost of time to compute gradients to the function, this is the thing that we're not going to see here, right? So this is all we want to say. But indeed, like maybe model compression will help, such that we don't go into huge parameter scales, and we can still do interesting things with machining. That's totally valid.
Right. And I think what you said about neural networks is very relevant for, like, you know, kinds of quantum simulation algorithms that I personally interested in. So I think there was another question about space efficiency and time efficiency. I imagine those are, you know, related to each other in the way that you could prepare identical copies versus a bunch of the same copy. But if you have any other comments, I'm happy to listen. Or
so what is the question exactly?
Is it possible to trade off between space efficiency and time efficiency, such as a hybrid method of backpropagation with copies and parameter shift?
Yes, good question indeed. And this is not something that like we kind of studied very nicely, but yes, imagine there are definitely space trade-offs and time trade-offs. In our algorithm, we kind of we just assume in full generality, like you know, states and what is the minimum kind of number of copies we would need to be able to compute all the gradients. Maybe if you have more copies, I don't know, maybe something more efficient or more interesting could be said. I'm not entirely sure, but it's a good open question, I guess. Yeah.
I love the open questions. Okay. Let's see. I think that's all. I had one. I want to puzzle you with something as well. So you were talking about this multi-copy access. Yeah. Could this multi-copy access, where you're doing measurements without throwing away the entire quantum system, could this be similar to the stabilizer measurements that are used in quantum error correction?
Oh, okay. So I don't know anything about error correction, but like, how do these stabilizer measurements work?
Right. So, I mean, you can think of it as kind of like a parity measurement, for example. So maybe you have like a Bell pair and you measure both qubits in the Bell pair and you see that the eigenvalue is 1, then you don't destroy the Bell pair, for example.
Aha, yeah, yes, this is okay. This is exactly the same concept, indeed. So like the schemes that like kind of exploit this efficiency in shadow tomography that we use rely on this Bell difference sampling primitive, right? Somewhere in there it requires this, which I think is exactly the same math going on with the stabilized measurements that you described on. Yeah.
Gotcha. Okay, cool. So there's like I always think there's like there's always some deep connection between these fields that you know.
Yes.
So
Yes, and I love yeah, I love these stabilizer states, and I'm learning a lot about them recently, and I think this is very, very cool. So yeah, indeed, there's like assets is all kind of the same. Yeah.
Okay, well that's great. I think we have you know, pretty much gone through all the questions. Thanks you so much for your answers. This discussion has been extremely enlightening, and I'd like to thank you from the IBM Quantum team and the Qiskit community as a whole. Thank you for being here. And I will plug for next week, IBM Quantum's own Elisa Balmer will be telling us about dynamic circuits for long-range entanglement. So thank you all. Come back here next Friday at noon Eastern Time, and either I or one of my lovely co-hosts will see you there. Take care.